Hello, everyone, and welcome to our Machine Control System course, in which we are about to study the next chapter, which is Chapter 7, which consists of two parts, which is Root Locus Sketch, and another portion is Locus Design, or you can say Design by means of Root Locus. So let's recap what we have studied till now. All right. So what we studied already was stability analysis, in which we studied the amount of poles and zeros and what they contribute in the stability of a system and how different system behaves. And then um, after discussing all of the details of stability, we uh, take an overview of steady state error. In steady state error, we consider stable systems and we characterize their uh, behavior using their system types and applied inputs, and we have seen various examples of that in the last chapters. So once we have covered all of the both the aspects of our the previous chapters, we are now ready for learning a new technique which is called the root locus technique. So why to learn this technique? It's quite simple because it shows you the behavioral system and the stability of system very effectively. So you can use root locus sketching techniques, which we'll study that what alternatives we have other than this. Another perspective of using this root locus technique is to design a system using root locus. So this is basically the major advantage of learning root locus technique. So traditionally, what we learned was we used to design system using random values of uh, zeta, initializing values of zeta. Of course, number one for the value of its stability, and then its characteristics, right? So in characteristics, we also learned that it includes peak overshoot, percentage peak overshoots, and all the residue characteristics that we studied in chapter 3. So we select an appropriate zeta for initializing a system, which a stable system, of course, and then we finally tune up to a value which is effective value of omega d or omega n, for which you can say that you have a very desired value of your settling time and rise time, right? So in that way, by initializing the values of zeta and omega, we are finally able to design a system using these two values and first clarify its stability, and then we can further move to the characteristics and well define the characteristics of a system. We can do the same thing um, using a root locus technique, which we will be seeing in the next chapter or next subchapter. So let's start. What is a root locus? All right, so we want to add a controller to the forward path of the system so that we can control its output. So you can see by this diagram there is a simple closed loop system in which consists of a plant GFS and a feedback HFS, and as shown here there is a all right. So we have a closed loop ratio here, and using this closed loop ratio we can define this closed loop system. But Let's say if the plant does not operate in a way which is required, or maybe I want to control it in some efficient way. So what I do is try to add here controller. Let's say GC is our controller, and let's add that controller. So I added this additional control to the plant in the forward path of this closed loop system, and I named this GC, and I call this a controller. So this can be another function, transfer function like GS, like there was GC, and this will help us control the characteristics of a plant in which we want to perform a particular operation. So GC, we have to design a value of GC. The parameters of the GC would be our design parameters, which would help us control the plant in an efficient way. So if I write the closed loop transfer function now for this function, this would be C over R times this, and we can easily see that GC is also, by simplifying it, GC is also present in the numerator as well as in the denominator. That significantly means that GC, which is the controller of the plant, this would contribute to the poles because it's present in the denominator, as well as in the zeros because it's also present in the numerators. So we can say the value of GC and the function which characterizes this controller would effectively um, decide the stability of system or characterize the stability of the systems. So of course, because the number of poles are given by this GC. So let's say if I start with a very simple controller, a proportional controller, which is a value of k, which is simple magnitude of some number, which gets multiplied by one function. And this proportional controller, when I simplify, gives me this closed loop function, which indicates that this k would help me define the poles of the system, and eventually, which means that it would also help us, or it would also contribute us to the system to define its stability and its poles, right? So this is how we add an additional controller to manipulate a closed loop function, which could help us attain a system's stability and desired characteristics of the system. Let's say, for example, if I have a controller K, and in the forward path I have a plant function GS given as 4 upon S plus 1 and S plus 7 and so on. And we have a unity feedback here as for standard. And let's say what happens if I simplify this equation. I can find out that when I write the closed loop function for this equation, we can see that if I put this structure and simplify it, I can see that k is contributing to the values of poles. And if I change the values of k for a particular range, let's say from 0 to infinity, or whatever range you want to select, when the value of k is changing, the number of poles, so the values of poles are continuously changing. So yeah, this lead us to a very important conclusion that by varying the values of k, we can change the behavior of the system. Even we can alter the stability of system. We can choose a particular value of system for which the system behaves as stable, and we can also choose values of k for which system is unstable, is not stable, and which is undesirable. So we want to avoid the values of k for which system gets to instability. So let's move forward. So what we are trying to do here is we want to change the values of k from let's say, for example, from k equals to 0 to k equals to infinity. And by changing those values, what we are trying to see is how uh, the location of poles are affected, right? So what I'm trying to do is I'll change my value of k from 0, k equals to 0 to k equals to infinity. So when I change this value from 0 to infinity, the Closed loop poles changes from let's say -1, -7 to onwards to some complex values. And by looking at the poles, and I can also compute the characteristics of the system, which is zeta and omega naught, or the natural frequency of the system. So we can see that for initial values of k, when k started from 0, system was overdamped, and as gradually the values of k increases from 0 to 2.25, the system was overdamped. But as it crosses the values of 2.25, at 2.25, k equals to 2.25, the system has repeated roots, which means that we have a zeta equals to 1 and we have a critically damped system, right? And as the system crosses the value of zeta, so the values of zeta gets less than 1, and of course we have an underdamped system, and then onwards moving to 0 we have an undamped system. So we can see, we can use k as a regulator. So as we tune the values of k, the behavior of the system gets changes, right? That's the idea. So let's plot these values of k for different values. When I change the values of k from 0 to infinity, let's see what a path it traces. So let's say these were the initial values of poles when k was equals to 0, and now these were the two initial poles at -7 and -1. So I plotted these values, and as I move my change the values from 0 to 1.25, the values get poles get changed and they get a little bit more close. And at 2.25, they overlap, of course, because that's a critically damped system. And moving forward, the values of k, now the values of poles get deflected in the vertical directions, though they were moving in horizontal direction towards each other before achieving 2.25, and now they're heading away from each other vertically after 2.25, and then they move onwards to k equals to yeah. So k equals beta equals to infinity. So we can say that they are these poles, by changing the values of k, we can see that these poles are getting um, the location of poles are continuously changing, and they are tracing a path. And we can identify that this pole, which started from the left, very left, started from here, and then it moves towards to the negative infinity. And you can see that this pole will start from very right, moves and moves up. So we can trace two paths like this one going to the right. So how I know this goes down? Because I trace the values of poles. So of course these values goes down, and these values of poles gets up. So this path is nothing but actually the loci, or you can say the path followed by the poles as I change the values of k. So this loci traced by the poles, or the roots, you can say roots of the system. So this loci traced by the root of the system is called actually root locus, right? So this is basically the definition of root locus, that root locus is actually the path traced by the values of system poles as the values of k approaches from 0 to positive infinity. So if you select the value of k equals to 0 and moves towards the values gradually towards k equals to positive infinity, the locus you will plot is called a root locus, and for which complementary root locus is something which you can say um, that if I change the values of k from k equals to 0 to negative infinity, then of course that would again be some another sort of loci traced uh, by the poles of the system. But in this situation we haven't plot that, but you can always plot that. So in that situation, when we move the values of k from 0 to negative infinity, that sort of loci would be called complementary root locus, right? So this won't be equal to the part we have shown here. This is actually the root locus, but yeah, we can always see that. So can I ask you, what if the system is stable or unstable? Um, yeah, so the point is that all of the roots, however I change the values from k, from 0 to infinity to whatever I want, the point is the roots or the poles of the system does lie on the very left plane, left half plane of the system, on the S plane, right? So we already know that when the system has its pole on the left half plane, so the system is stable. So that means whatever I do with the value of k, the system is always stable, right? So that root locus also tell us that in whatever variation of k, let's say, so the system would be stable. So for example, how we're going to use that? Number one is to design a system. Of course, we want to design a system. Let's say k is some physical parameter which changes with temperature, and we have a change in temperature from summers to winters, and for every, let's say, change of 5 degrees centigrade, we have a 10% change in the value of k. And we want to make sure that throughout the day, throughout the year, when the temperature changes about like 20 degrees, maybe. So we want our system to behave perfectly, because that's going to be subjected to a times percentage 10% change every time per 5 degrees centigrade. So that's going to be a big change. So we want to design a system that could perform well in every sort of situation, and we want our poles to be lying in the left half plane of the system, so the system is always stable. So that's the perspective we will be doing when we are designing a system. And of course, if let's say the situation till the situation we want to study the effectiveness of a system, so we vary the value of k, and we want to study how the system behave, and how different characteristic it has at different values of k. Like we've already seen that the different value of k system was critically damped, and before that it was over damped and under damped. And so we can fine tune and study a system, or in different configurations and different variations. So in that perspective we can use the system. So both of the aspects are quite important. So, number one, how to find this root locus? This is a question of interest, and I think there can be a lot of methods which comes to mind of mathematicians. That number one is, of course, to use some computing method, which is the modern technique, and of course, MATLAB is one of the most strongest language, so we can use always our system command like R locus. We define system in terms of two arrays, two vectors, and of course, number one represents the numerator, and the second one represents the denominator. And yeah, we can define the transfer function, and then we can take the root locus. That's the simplest way we can do. But there are another methods, let's say analytical methods. So of course, analytical method is somewhat relevant to what we have demonstrated a slide back. So this, by changing different values of k, we plot different values of poles, and by those placement of poles we can track out a loci, which gives us information about the root locus. But sometimes it's quite hectic to find out manually the poles, or you can say the roots of the system. So well, we can use analytical, some rigorous methods and approximation techniques to find out those roots if system is quite complicated, not simple, right? So one of the methods I propose in RE transaction of automatic control is demonstrated. If you want to take a look, it's a good approach. And then finally, we come to the scope of our subject, which is quite easy and quite simple, but not complete in a sense. But yeah, that would give you a fine perspective of how to deal with some fundamentals of root locus, and I think that would be quite helpful. So we will be quick sketching the root locus, and we'll study some fundamental rules to draw a root locus. So how to draw a root locus without manually calculating the values of poles and plotting it, right? So there would be like thumb rules. So um, then moving forward, we start with rule number one. So we'll start with sketching the rules. Rule number one says As the value of k increases from 0 to infinity, the roots move from poles of g of s, which is your open loop system, and to the zeros of system. So that's a sometimes a complicated to understand. So what I'm trying to the point what I'm trying to make is quite easy, and not I want initially I don't want you to go too much into complexity. So let's say what I'm trying to tell you is that's a zero and that's a pole, and whenever you have a pole, so this system says the roots move from poles to the zeros. So of course these poles are of g of s, which is our open loop system or open loop pole. So these poles which are obtained as a result as an effect of this open loop are called open loop poles, and the zeros obtained by g of s is called open loop gain. That's why it's simply terminology. So we can say that the poles move towards the zeros. That's the fundamental, right? So whenever we see a pole, usually, right? So not exaggerating, but yeah, most of the time when you draw a pole, it's always heading towards some zeros. So sometimes there can be zeros which are practically there, and sometimes there might be zeros which you can't see, and you assume that those zeros are somewhere at infinity, right? So we will study that. What does that mean? So the point is, whenever there's a pole and a zero, we draw a line from pole to the from the pole and terminate that line to zero, which indicates when k was equals to zero, uh, or k equals to zero is actually the start of root locus, right? So when we start root locus, um, we start with the value k equals to 0, and as we end root locus, we have k equals to infinite. So at k equals to infinite, the value of roots would be at the position where you is your 0, and when you start a root locus, the value of k is 0, so the value of roots would be exactly where your roots are. So how the question is why, right? So I don't trust you. I'm saying this, but let's say you don't trust me. So yeah, so all of the next explanation is to defend that why should we draw um, root locus from poles to 0. So we will discuss this why we are going to do that. So it's quite simple, like in order to see that, like if you trust me, let's say, so you can easily like follow this rule, and that's not very difficult to figure out. But let's say if we want to investigate that, okay, let's prove why should we move from poles to zeros. So yeah, we need to look at some of the mathematics to understand that. So let's explore this. All right. Oh, why don't I select? All right, cool. So let's say we assume the simple proportional game controller, and like we have seen this controller before, we can like write its open loop gain as k g of s, and we can like write its closed loop gain as k into gs upon this whole factor, and open loop gain into k into gs, because that's the system when your unity feedback is open, and if you see unity feedback gets multiplied with k and gs, so you can say that there is just one here of h of s unity feedback, which is getting multiplied with this, right? So this is getting multiplied with 1, and of course we get the same result. And by that we can say that let's assume that g of s is our open loop gain or open loop system, and we can characterize, we want to subdivide the system in the form of numerator and denominator, let's say, right? So I'll call the numerator as a polynomial n of s, and I'll call the denominator as a polynomial which is d of s. And we know that if I equate it with 0, I'll get poles, and if I equate n of s with 0 I'll get 0. So I think that's quite simple. Yeah, so remember this, onwards we are going. So whenever we equate n of s with 0, that means we are trying to figure out the values of zeros. And when we are trying to equate the values of dfs to 0, so we are about to evaluate the values of both. So all right, going forward, so you can see right here that by simplifying, if I want to find the poles of the system, I this is my characteristic equation. And if I want to know the values of poles, I know that I'll have to solve this equation and find the values of s. And I already know that g of s was actually equals to this whole factor which we studied a little bit earlier, which I demonstrated. So I just substituted that value so that I can have a discrete understanding what I'm the point I'm trying to prove. All right, so we have this equation, and we can always like multiply these dfs with 1 and simplify this equation, and I'll get this equation. All right, so we have this CE by simplifying this equation to this equation, and we can find the value of k using this. So we can see when I derive this equation for k, it gets d of s upon n of s, which is actually denominator upon numerator. And if you remember, the conventional g of s was actually n of s upon d of s. So that's quite opposite if you see, right? That's quite interesting. That means when I make when I try to find zeros, I put this value to 0, right? And when I put dfs to 0, k becomes when this becomes 0, k becomes infinite. And when I onwards move to dfs tends to 0, let's say, so I'm actually trying to find out the poles. And in that situation, you can say when I'm trying to find poles, the system will get dfs will get 0. So I can say for k equals to 0, I'm finding the poles. And you can say that for k equals to infinite, I'm trying to find the zeros. Right, so we have concluded much. We can say for zeros, n of s approaches to 0 and k approaches to infinite. We have already seen that. And for poles, d of s approaches to 0, which means that k is equals to 0. So that's quite a bit like a little bit maybe sometimes confusing. So take your time and recall this. You can always go back to the video and slow down the process, and you can calculate it yourself, and you can see that why the value of why we have a value k equals to infinity when n equals to 0, and when why we have a k equals to 0 and d equals to 0, right? So that shows us that when k equals to 0 is actually the beginning of root locus, and k equals to infinite is actually the end of root locus. So um, we can say at the beginning of root locus, when k equals to 0, we start from the poles, and at the end of the root locus, we end up at k equals to infinite, which is the values of zeros. That's why we always want a root locus to point from poles to zeros. All right, so what does that mean? In one other perspective, let's see. So that simply means, which I told you, that as k equals to 0, we can say, of course, when denominator gets 0, so we are at the location of poles, and k equals to 0. Likewise, when we have k equals to infinite, it's the end of the root locus. And we can see here, if I put k equals to 0 in this equation, this whole factor gets 0, and I'll get d of s equals to 0, which means that poles get dominant and zeros get less dominant. And we can see that the location from where we start our loci is dominantly affected by the values of poles. So Yeah, it's quite simple that if we substitute the value 0, the all the parts, all the effect, all the features, characteristics in the numerator gets cancelled out because k in this k equals to 0, and only factor that affect this characteristic equation is your d of s, which is actually the values of poles, right? So d of s equals to poles. The poles get significant when k is equals to 0. And when k is equals to infinite, you can see that although d of s is there, but when infinite is multiplied with d of s, which means that the characteristics of the numerator is greatly amplified because all of the coefficients will be multiplied with infinity and they would be have a very large number, and you can say that significantly d of s is again present there, but um, n of s, which is the numerator, would get dominated, right? So in this situation, when k is equals to infinity, the zeros would be dominant. So what we can conclude is when k equals to 0, poles were dominant, k equals to infinite, zeros were dominant. So from k equals to 0 to infinity, we start from poles and terminate or end up towards the zeros. So let's conclude at this. I just wrote it down for you just in case you want to remember. So root locus starts from the values of pole of g of s and ends with the value of g of s. So this is just the analytical explanation of the simple points. Then that whenever you see a pole and a zero, you sketch a line from heading from the poles to the zero, which means at k equals to 0, root locus was at the location of poles, and as k equals to infinite, it approaches the values of 0. Yeah, so that's quite simple. So in that scenario, um, we will move to our next slide, in which we have to see some quick examples, and then we will move to the next row. So let's say if the number of poles is equals to number of zeros, let's say I have a one pole and one zero. So what? Take a minute to uh, think about what could be the sketch for this graph, right? All right. So we can see that from poles, there's a pole up here and a zero up here. So we can say the poles are all on the negatives, left half plane of the system, so the system is stable, and the root locus start from the poles and went towards the zero. So I can say that it's simply from poles to zero. This is a simple root locus sketch for this graph. And what about if I have two number of poles, and let's say if I have two zeros and one pole. So in that situation, what could be the case? So in that case, we have to assume something that for every pole, we have every zero, right? So of course, we can't see a zero here for one of the pair, for one of the poles at least. So we will assume that there is one pole, one zero at infinite for the particular pole. So let's say if I have two zeros here and one pole here, so I would assume that one of the zero will be paired with this pole, and the zero which is left out is paired with another pole which is resting at infinity. So of course, like we can say that there is a hypothetical pole at infinity resting in this case when number of pole is less than number of zeros, and when the number of poles are greater than zeros, we'll assume that there is an imaginary or not imaginary, basically hypothetical zero paired up with one of the poles which are present here. So of course we can draw that in such a way that we assume that this pole gets towards zero and the root locus, and this is also approaching towards the zero, which is actually hypothetically present at infinite, right? And same like the case we have studied, we can generalize that this pole approaches infinite, and of course there is one more pole at infinite, so the arrow or the root locus is coming from that pole on infinite towards the zero. So that's the easy way to understand this. So I call this a lost friend. So we'll also summarize that a lost friend is something which is not present here but somewhere present in the infinite, and this pole or maybe this pole and this zero are looking for the lost for that lost friend. And this is an easy way to remember this. But yeah, that can be exception. There can be exceptions. We would be, which would like maybe confusing. But yeah, don't worry about that right now. The simple idea is till now is that every pole approaches to a zero, and if there isn't a pole pair, complete pole pair, let's say there is no zero for a pole, or maybe there is no pole for a zero, so we would assume that its lost friend or the lost pair is at infinite, and we'll draw the sketch accordingly in that configuration. So that's it for rule number one, and we'll study rule number two and onwards in the next lecture. Thank you.